Pleasure to introduce our speakers for this session. Kevin Janus is a business development manager for Reliant products. He received a Bachelor's of Science degree from the University of Wisconsin-Madison, where he majored in chemistry and philosophy. He also received his Juris Doctor from the University of Wisconsin-Madison School of Law. Kevin has been involved in aluminum finishing for 21 years. He became involved with aluminum finishing as an assistant research chemist at UOP, developing novel coatings on aluminum. He became involved in anodizing at Linetech, where he served as the anodizing technical manager. After leaving Linetech, he consulted to Reliant, serving as the marketing manager and technical services manager for the aluminum finishing segment for all of Asia. He has been the technical sales and service agent for the Upper Midwest for Reliant products for the past 15 years. Throughout his career, he's been involved with continuous improvement efforts, including Six Sigma and lean manufacturing. Jacqueline Cook joined Reliant Aluminum Products in 2018 as a lab chemist, focusing in specialty shade matching, troubleshooting, and chemical analysis. As a part of the technical services department, she provides both in-house and on-site technical support and expertise to Reliant's customers. Jacqueline previously studied environmental engineering at NC State University. Welcome, Kevin and Janus. I'm turning it over to you now.
All right, thanks, Dave. My name is Jacqueline.
And I am Kevin.
And we're going to be working with the analysis of multi-component dye baths using CIE Lab and Reflectance Spectrophotometry.
So one of the things that got us looking into this project is trying to develop a way of controlling dye baths with multi-components. And historically, they're very, very difficult to maintain for a number of factors. One of them being disproportionate consumption. So one of the dye components will be consumed at a higher rate than another component, and that will shift color. One of the components may be more vulnerable to the two big contaminants we face on anodizing line, aluminum and sulfate, and also just basic decreased activities of one of those components over the other one over time. And so as a result of this, we've kind of started to go away from doing mixes of dyes, and definitely we avoid dyes that have really significant components, 3 or more, where we won't even recommend those. So we were going to originally look at these things using transmission results, but Jackie in the lab found out that really didn't seem to yield any kind of practical results, as the transmission results were not correlating with what we're seeing on the actual anodized parts. And as we all know, that's the important thing. It's not what the dye bath readout is, it's what the part actually looks like. So reflectance values are probably a better way and more accurate way of detailing what we actually see and the deviations from our standards that we can't even start to see with our eye. So hopefully we can pick up on those color changes before it's too late, before the parts have gone out to where it's going to be a problem to the end user, to your customer.
In my experience with designers, designers love the look and the feel of anodized aluminum. They feel that the material and the finish exude a feeling of value and of quality. So when you present them with this material, they're really excited about it. Then they always will say, can we get it in this specific color? And it's usually a color that's not part of our standard palette of dyes. And then we say, well, no, we really can't do that, or it's really difficult to do that. And but here are the colors that we can do. And they will typically, if they're really sold on the color, then they'll end up saying something along the lines of, well, yeah, this is really interesting, but we're looking for this color. Now, it doesn't mean that they're not going to necessarily come back to this and come back to anodizing in the colors we can usually provide easily to them. But it's something that's going to be on the back burner. It's going to be underneath a pile of other things. It's going to be potentially forgotten, and that opportunity to enter a specific market, to maintain a market share, is going to be gone. And one of the problems that we have in this industry is that the competitive finishes and competitive materials can offer a lot of colors. Paint, the colors are virtually infinite. Plastics are becoming much better, and they have a almost infinite palette selection as well. And you can't discount how plastics and polymers are coming around. It's my understanding that in the firearm industry, for your assault rifles, your AR types, the lowers that are usually made out of aircraft grade aluminum can be made out of a polymer. So that's quite an advancement. So we're going to be starting to see polymers and plastics enter our areas that we are currently in and compete with us in this color. So it becomes a very, very important thing to try to increase color capabilities. This project was designed to try to see what the feasibility and the practicality of developing means of analyzing multi-component dye baths to make the process control more robust, so that we can achieve and maintain custom color blends. But even some of the blends that we already offer that are a multi-component type of a dye, like a green, if we can develop this type of an analysis system where we can start to head off at the pass, if you will, when we start to see where we're going to start to see a color change, it's going to take us outside of the acceptable variation. So this is another reason it will go beyond just looking at new colors. This will hopefully even help us maintain our existing colors to a more precise amount, because again, the competitive finishes that we're up against can achieve much, much better color variation or lack of color variation. And hopefully, ultimately, we will be able to create a system of control where we can start taking and achieving all kinds of new colors with custom dye blends, and be able to actually maintain those in a way that is competitive in terms of the variability and competitive in terms of the cost. You won't have to make up a dye bath, and once the color shifts, you'll have to dump it and start all over. We can hopefully maintain these dye baths over time to drive down that operational cost associated with these these new colors and these other color palette opportunities.
All right.
Yeah, from here I'm going to turn this back over to Jackie, and she's going to go over all the experimentation she did in the lab, and she's going to start out with a little bit of a background on color. Thank you, Jackie.
Thank you, Kevin. So before we get into the experiment and everything, we are going to do a little bit of background, starting with color theory. So color theory can be a little bit confusing for those of us who are more technically minded, but because it has a lot to do with the visual aspects of it. So before we begin, we're going to kind of go over these terms: lightness, hue, and saturation. Lightness is how bright or dark it is. Hue is where it falls on the color wheel, and saturation is how vivid or dull it is. These terms, they are relatively self-explanatory, but when you can know the difference and know how to describe what the deviation from the standard is using these terms, it'll be easier to use the data later on as well. So if you look at the right here, you have these two balls. Can you tell the differences between them? Is one brighter or more vivid? Is one darker or more dull, etc.? Are they the same hue? So kind of think about that. All right, so as you can see, the top one is lighter and more vivid. The bottom one is darker and more dull, but they are the same hue. They're the same color, essentially. So now that we kind of have those terms in our mind, we're going to try and visualize them. At the top here is that aforementioned color wheel. It's really important to know how these colors interact with one another. You'll be able to translate that information into how using different multi-component dyes can affect one another. For example, if you have a gray dye that has a reddish tint to it, but you don't want it to be that red, you want to neutralize the redness, you would add something on the opposite end. You would add a green or a blue-green to neutralize that. And going along with that, if you want to shift it one direction or the other, you want it to be slightly more orange, you'll add yellow. If you want to shift it slightly more purple, you'll add blue. So that's really important to kind of keep in mind. The bottom part of this here shows us how these colors interact with lightness and saturation. So at the very center of this, again, that green and red, at the very center, they cancel each other out. So they are very dull and there's no vividness to the colors. It's basically gray, it's achromatic. At the very top, it's white, and at the very bottom, it is black. And then if you go around the edges, you can see how it's like a darker green or a darker red, etc. So now that we've kind of armed ourselves with ways to define colors, we can look into color spaces and define or assign numerical values. So color spaces are methods for expressing the color of an object or light source using some kind of notation such as numbers, so we can quantify what we're looking at. So the most commonly used color spaces are the LAB, which is probably what you all are most familiar with, and the LCH color spaces. And we're going to go into a little bit more detail what these mean, how these numbers apply. So starting with the LAB, or CIE lab color space, as it's also called, we have these three notations. First, there's L. This ranges from 0, which is white, to 100, which is black. It is that vertical z-axis. Then we have that first horizontal axis, x-axis, which is A. This ranges from a negative value, which is green, to a positive value, which is red. And then conversely, we have that B, or the y-axis, which goes from a positive yellow to a negative blue. If you are looking at, like, say, a delta L or a delta A, these numbers can be, again, positive or negative. But for L, it'll always be 0 to 100, always positive, unless you're doing a change in L, which means it can be negative. I hope that makes sense. So first, we are going to kind of look at that ball from the first screen. Are you able to pinpoint where it would be on here? Would the L value be closer to 100 or closer to 50? Would the A value be positive, meaning it's more red or more green? Does this shift a little more yellow or a little more blue on that B axis? So I'll kind of let you think about that for a moment, see if you can figure out generally where these numbers would be. All right, so this is generally where this would end up. The L value is 43.31, so it's pretty close to that central axis. It's pretty vibrant. That A value is positive 47.63, which means it's mostly red, which makes sense. And that B value is positive 14.12. So it shifts us a little bit more into an orange region rather than a pinkish blue region. Just for another example, just to make sure we kind of have a grasp on how this works, I'm going to show you this one as well. For this, will the L value again be, will it be darker or lighter? Will it be closer to a greenish color rather than a reddish color? Kind of think about that for a moment. Also keep in mind that when you are doing reflectance values, shinier surfaces are harder to work with as the color bounces off more, but we will go into a little bit more detail about that later. All right, so here are those values. The L is a little bit darker than before. It's at 57.4, which means it's closer to black. The A value is negative 15.64, meaning it's shifting slightly to that green area. And then the B, the more dominant color, is at negative 40.33 because it is very blue. All right, so now looking at this other color space briefly. This one we're not going to use as much, but I think it's important to kind of have this in our minds. So again, we have that L value, which would be that central axis going from 0, which is white, to 100, which is black. C is chroma. So chroma actually represents, it's a distance from that central axis. So the higher the C value, the more vibrant the color is. Then we also have hue, which instead of being just a value on a random part of the graph is actually an angle. So you start at that positive A or x-axis and you go counterclockwise clockwise like you would for polar coordinates. So if the H value is at 0, that means it's red. If it's at 90 degrees, that means it is yellow. Going over to 180 degrees, which you can't see on here, it would be probably around green. And then circling all the way around to 270, it would be blue. All right, so again, looking at that ball, can you like generally figure out where these colors would, this color would land us? Would that L value, which should be the same, where would that land? Would the C value be more vibrant or is it more dull? And that H value, what would that angle be? And I'll let you kind of think about that for a sec as well. All right, okay, so here are those values again. The L value, again, is 43.3. Our C value, it is a pretty vibrant color. It's close to 50 at 49.68. And that H value is a relatively small angle, 16.5. So it's that red kind of slightly moving into the orangish region. All right, so now that we have that, let's go over wavelength and reflectance. Color, as you know, is probably defined as the humanized perception of reflected radiation in the visible region of the electromagnetic spectrum. This ranges from 400 nanometers, which is near the UV light, more purple, to the infrared at 700, which is red, obviously. And then if you know the rainbow, it kind of fills itself in from there. So when you look at reflectance data, which we will be looking at, you'll be able to see how that interacts. So as Kevin mentioned before, we were going to try and do this project using transmission. Transmission is analyzed by projecting a light source through a sample, and then based on the absorption of the beam at a specific wavelength, that kind of gives us a number at this frequency of light. Conversely, we have spectral reflectance, which is a measure of how much energy as a percentage a surface reflects at a specific wavelength. And that's kind of more of the information we're going to want to work with. We did really want to work with transmission for this, but it did become immediately clear that that wouldn't give us like viable or accurate readings for how we need to adapt our bath over time. Okay, so looking a little more into reflectance. Reflectance data can be obtained using a spectrophotometer standardized with a pure white standard, which is 100% reflectance, and a black box, which is 0% reflectance. Now, think about it this way. If you have a white surface and you're bouncing a light off of it, the light will bounce right back, 100% bounce back. On the opposite end, a black box will, if you shine a light to it, nothing will bounce back. It completely absorbs it, so there's 0% reflectance. These readings will end up producing a spectral reflectance graph, like you can see on the right here, where the x-axis is wavelength in nanometers and the y-axis is percent reflectance. And we're going to be using that data to adjust our baths later on. All right, so here's a little bit more of a close-up. As you can see, we have that white at the very top at 100%, it's just a straight line. And as well, the black at the very bottom at 0% is a straight line across. You can see this gray curve in the middle. That's not really a curve. It kind of just waves in the middle. That's because there is no saturation of a specific color. It's neutral, but it is lightness-wise in between that white and that black. You can also see here the peaks. So if you were to do a blue sample, it would peak right around here between 430 to like 490 nanometers. The green peaks around 510 to 550 nanometers, and the red peaks between 610 going all the way up to 700 nanometers. Now keep in mind that you can see the red is higher up on the reflectance percentage. This is because these colors appear brighter between yellow and red. They appear brighter to the spectrophotometer. Meanwhile, the blue will always appear a little bit darker, so the percent reflectance will always be a little bit lower on the graph. All right, so now that we kind of have that information and we're armed with it, let's go into the actual experiment. We wanted to start with a dye that has a tendency to kind of shift over time pretty easily. That is green AEN. It is really popular, but it has some issues that I'm sure some of you have dealt with in the past. For the reflectance graph for this, here it is. It peaks right around 520 nanometers, which if you can see at the top is that green range, slightly on the bluer side. So let's kind of work with that data. Before we really, oh, that's a little off. Before we begin, I did want to kind of visualize and see differences between having the standard and then having samples that are slightly more blue and slightly more yellow. This two-component dye is made up of a blue and a yellow. So what I started by doing is making a sample with more blue in it than the yellow, and then conversely, one with more yellow than the blue, and then doing those readings to see what the differences will look like on a graph. So here is that data there. The blue, as you can see, does shift slightly to the left, but there is no significant change in the percent reflectance at the peak. And then we have that yellow, which shifts slightly to the right. And then, as we said before, the yellow to red area always has a higher percent reflectance because for some reason the spectrophotometer thinks it's brighter, it sees it more. So that percent reflectance will be higher up. And then it is well shifted to the right. Keep in mind when we're looking at these graphs throughout this presentation and then in the future, if you decide to utilize this, you're going to want to look at the peak or potentially multiple peaks and the areas of transition on them. That's where you should see the biggest changes, and that's the information you're going to want to use for when you adjust your bath later on. Okay, so when we started, I just wanted to do bath exhaustion to start. What we ended up doing was making a 2 gram per liter standard, a very small bath of about 50 mils, and then just running parts through it continuously to see if one part of the dye got exhausted more than the other. So we ended up running about 150 square inches of parts through this teeny tiny bath to see if significant changes could be seen. And we ended up doing a reading. If you can see this lighter curve here, that is the sample. So it did give us some pretty interesting numbers. For the most part, there's an overall lightening. You can see that delta L is positive, which means the part is significantly lighter. And this most greatly affects our delta E. If you don't know what delta E is, that is the overall change. It's basically an accumulation of those LAB numbers. So the overall change from the standard. I would recommend keeping this below 4 if you're going to run it on the line. So having this value be at 8, it's double what we would want. So what we ended up doing with this was doing about a 27% add of our green AEN to bring this back to normal. That ended up shifting the curve back down, and we were well within the boundaries we want to keep it close to the standard. And as you can see as well, the delta A and the delta B numbers, this shifted slightly more yellow, but it wasn't significant enough to warrant adding blue to adjust it. All right, so next we wanted to work with contamination. Now, as many of you know, contamination can be incredibly detrimental to these dye baths, whether it's sulfates, aluminum, etc. So what we ended up doing was adding about 1,000 ppm of sulfates to a fresh 2 gram per liter bath, letting it sit overnight, and then doing a dyeing in the morning to see how this would affect the color. So you can see here, the curve is a little bit higher, and then it shifts a little bit to the left, meaning that the part looked a little bit more blue. And that also tells us that it affected the yellow in the bath more than it does the blue in the bath. The biggest numbers you're going to kind of want to look at are that delta L, which is 1.96, and then that delta B, which is negative 2.01, saying that it shifted a little bit more blue. Surprisingly, this dye wasn't as affected by contamination by sulfates as we thought it would be, which is actually a great thing, but it did kind of mess with the experiment just a little bit. We did end up adding about a 4 to 5% add of the yellow and a 15% add of the green, and that kind of brought our curve back to normal, and everything was well within range. For the final part of working with the green, I wanted to take a random customer bath that we just had lying around in the lab, doing a dyeing after adjusting the concentration to 2 grams per liter, doing a dyeing and comparing it using the spectrophotometer. So as you can see here, that delta E is pretty high. It's at 6.67, and it's mostly affected by that delta A and that delta B. So looking at that delta B first, it's at around 4.6. This means that the part is significantly more yellow than the standard. Also looking at that delta A, it's positive at 4.4, which means it's more red. For a green dye, this basically means that it's not green enough. The saturation of the green just isn't there. And it'll be interesting to see if we can get this back to what we want it to be. So we started this by making an adjustment of about 10% add of the blue and an 8% add of the green to adjust that strength to see if we could get it back to normal. And this is what ended up happening. So we got the delta E back under 4. You can see that delta B there is negative 0.29. So the add of the blue brought it back, but that delta A is still really high. It's at 3.82. This is telling us that this green just isn't that saturated. And this is probably a result of use and contamination over time. It's not exactly something you can bring back from after it gets to a certain point. Contamination, once a bath's contaminated, it's contaminated forever, unfortunately. But this bath overall is well within range for what we want it to be. All right, so next we are going to look at a specialty dye mix that we actually get pretty frequent requests for. It's Coyote Brown. It is a military spec. It's a relatively neutral, dirty, bronzy, gray, brown color. That was a terrible description. But for this specific match, we've made recommendations using a combination of our 2 dyes that we have at Reliant, bronze 2LW at 40% and then 60% gray HLN. The bronze 2LW is a reddish bronze. So if you see the knife on the left, that one probably has a little bit more of that color in it. And then that gun on the right is a little more green. So it has a little bit more of the gray in it. If you can think back to the color wheel, the red and the green are on opposite sides of the spectrum. So they kind of work to neutralize and cancel each other out, providing that kind of more neutral clip that we see in the middle. This spec isn't incredibly specific. So you can see that the colors can range a little bit depending on what's happening in your dye, but you want to keep it within this range. So looking first at, there it goes. Looking first at the reflectance data for the standard, you can see that there are very tiny spikes at around 390 and around 520. That's like a little bit of the bluish purple and a little bit of the green that you can see in those parts. And then obviously the biggest spike is all the way over at 700, that red that's popping out, that the spectrophotometer sees as brighter. It's really popping up there. So as I mentioned before, you're going to want to look at the peaks and the transitions to see where the biggest changes are. Similar to the green, we wanted to do one sample where the dyeing was a little bit more gray and one sample where the dyeing was a little bit more bronze, and see how that affected our reflectance data. All right, so here that is. As you can see, the bronze has more of that red hint to it, so it is higher in that range between 650 nanometers and 700 nanometers. And then on the opposite side of that, the gray, which has that green on it, will neutralize some of the red and bring it down. So you can see that gray part of the graph is lower than the standard. So the biggest changes you'll see will be in that area. That's what we're going to want to look at working with this color. So to start, we didn't end up doing an exhaustion of the bath. We were a little short on time with this one, so I jumped straight into working with a contaminated bath. We once again added 1000 ppm to a 2 gram per liter, very small sample, left it overnight and see how it compared. So according to this graph, as you can see, it is significantly lighter. That change there is about, I would say, 10%. And that's pretty big. So what we ended up doing was doing first an add of 1 gram per liter to see if we could bring it back. And then we moved along and added even more. We ended up doing 110% add, so 2.2 grams per liter to a 2 gram per liter bath to get it back to the standard. And at that point, if your dye is that contaminated or that affected by contamination, it would be best just to dump it and start over, but for the sake of science. All right, so for the final part of this, I had a colleague make up a random bath, told her to keep it at 2 grams per liter, And we just wanted to see if I could bring it back using the data that I had and the relatively new knowledge of working with these dyes and these reflectance graphs. I wanted to see if we could bring it back. So as you can see on the curve to the right, the sample is significantly less red and significantly more blue. If you look around that 450 area and then going over to that 650 area, it is very big changes. You can also see this looking at our LAB numbers. So that delta A is at -6, basically, saying that it is significantly more green, and that delta B is at -9.5, so it's significantly more blue. If you remember looking back at the changes, this will tell us that this dye has significant amounts of gray in it compared to the bronze. All right. So working with that, I kind of used my knowledge on how these graphs work, and we did about an add of 40% bronze to LW, hoping to bring it back to normal. And because we were doing this in a lab setting and the dye bath is so small, we did also a slight dilution to bring some of the concentration down so it wasn't quite so dark. This ended up leading us here. So we got that delta E back under 4 like we wanted. The delta A is at 1.46, so it's like got a hint of red to it, even though it isn't quite showing on the graph, interestingly enough. And that delta B is -1.27. So it is a little bit more yellow. So we did bring this back. It was a small win for us. All right, so for the final part of the experiment, we wanted to work with black MLW. Now, black MLW is a pretty popular 3-component dye. It is mostly made up of a blue-black, about 90% of it's a blue-black. And then the other 2 components are a mixture of an orange and a reddish-brown. Thinking back to that color wheel, we know that orange is on the opposite side of blue. So it helps to cancel out some of the blue and neutralize it a little bit and gives us this really beautiful black that we can use for many different purposes. You can see the wheel, this part on the right, and the scooter. So it gives us a lot of options. All right, so here is that curve, similar to the gray that we saw much earlier thinking about reflectance graphs. It is relatively flat, going between the beginning of the graph around 360 all the way over to around 660 before it spikes at the red. That red is the most visible, and that's a result of the little bit of red we put in there to neutralize it. Also keep in mind, we did end up doing this black MLW at 2 grams per liter. I wanted to be able to visualize the changes as I was working with it, so we kept it there, but this will be applicable, I believe, also at 10 grams per liter, like you're running a regular black. All right, so like we did with the green, we wanted to start by doing bath exhaustion. I wanted to see if any one dye is used up more than the other. As you can see, after a little bit of time running parts through, the biggest change is that delta L, which means the dye was just getting overall weaker, the dye was getting used up, and it was at 7.24, and that most greatly affected our overall delta E. The other pretty significant change, though, is that delta B, it's at almost -2, which means it is more blue. This is telling us that the red and the orange in the bath do get eaten up faster. So we started by adding about 40% MLW to bring this dye back to normal, and that gave us this graph here. So the delta E is still pretty high, and this actually added more blue back to the bath as well. So our delta B got even a little bit higher. To work with this, we added a very small amount, about less than 0.5% combined of the orange and the brown, to bring that number back down. This did eventually bring our delta E back to 2.6 and our delta B, I think, around -1. So it got us back to normal, which was really good. For the next part of this, we wanted to do contamination again. Unlike with the other 2 dyes, MLW is most greatly affected by aluminum rather than sulfates. So we ended up contaminating it with about 100 ppm of aluminum, left it to sit overnight, and then again did a dyeing in the morning. So as you can see here, Sorry. As you can see here, our sample is significantly more blue and significantly less yellow and orange. This is also pretty visible in the numbers. That delta L is weirdly high at 7.24, and that delta B is at negative 1.9, so it is more blue. To compensate for this, we added about 1% of the orange and the brown combined to bring it back. And this actually took it to be a little bit more yellow. So to compensate for that, we added more of the blue-black majority to bring it back to normal. And that gave us these numbers here. So we got that delta E under 1, got the B value like very close to 0, and that delta A, it is still slightly more red, around 0.96, but the delta L is also back where we want it. So overall, that was a success. For the final part, working with the MLW, we again just took a random customer bath we had lying around. We don't know how old it is, how contaminated it is. We just wanted to see if we could work with it and bring it back to normal. The most significant changes on here is that negative 5.25 and that delta B at negative 7.9. Oh, also keep in mind, we adjusted the concentration down to 2 grams per liter so that it was the same as the standard. So with this, first we wanted to kind of work with that negative 5.25. We did a slight dilution of about 10% to adjust that. And then for that for that blue, see how it's going much lower on the red area? We had to kind of do an adjustment there. So we did an add of 1% of the orange and 1% of the brown. And that actually gave us these numbers. So this was, I think, the most successful, surprisingly. We got our delta E to under 0.5, delta L at 0.5. Our biggest change is still that negative 0.95, which it means it's still a little bit more blue. But overall, it was hugely successful. And so that is basically it for the lab side of things. And I'm going to turn it back over to Kevin to talk about practical applications.
Thank you, Jackie. Just kind of a quick note, something we probably should have mentioned, but we didn't put it in the presentation exactly, and that's the equipment that you would need to do this. Really, we implement 2 pieces of equipment. One is to measure the dye bath itself, and that's just a UV Vis Spectrophotometer. And the latest thing I think I priced one, or had someone price one brand new, was something around $2,800. I just did a quick eBay search while I was listening to Jackie, and you can spend on a used piece of equipment anywhere from $750 to $7,600. So it probably depends on how much capability you need. You don't need a lot for that end of it. And then the other thing is the spectrophotometer she's using to do the readings on the parts. And those, it's been a long time since I priced one of those. I remember like a simple colorimeter brand new from Minolta being somewhere around $2,000 or $3,000, but they've gone up quite a bit in price. But you can get the same thing. You can spend about as much money as you want to on one of those pieces of equipment. And that may be something for a future presentation by one of those equipment manufacturers to kind of look at this and give some options. Not being an equipment into things, I can't really comment too much, but you would need some equipment to do these type of things in a practical application. So what's in front of you from the pictures here is a customer that does some work with gray dye. And this is a very high-end marine application, very expensive boat. So you can imagine that the demand to have a good color match on anything that you do is there because people are spending a lot of money on these boats. And what it is, this is actually like an example of a single component contamination problem. So to control that color in gray, I think most people know that grays are very difficult to deal with in terms of color changes, because of now some of the aspects of the physical chemistry of the gray dye molecule, but also because our eyes are very sensitive to changes in gray. If you can research this, I was on the Minolta website and just looking really quickly, they had a nice little diagram about color sensitivity for the human eye, and you can look and see that gray has a very, very small circle in which the delta changes in any of the color things will show up for your eye to see it. So we see changes in gray, which makes this very difficult. So this is an actual application of this process where the original concern was that the dye in other areas that this particular customer had worked in before would shift to red. So they're very concerned about it going red or maintaining red. And based on how their line functioned and the contamination, he had more of a problem, not with redness, but blueness. And so then he uses this type of a methodology to control by adding usually yellow dye to control that blueness. So if you go back and you looked at, if you remember, Jackie had given that color wheel that shows kind of the way to combat a certain colors with an opposite type of a color. And if you're looking at blue, it's an orange or yellow that you use to shift it to kind of neutralize that blueness. And so by doing this process, they're able to produce, for a gray dye, they're able to maintain it with a nice long life, and they're able to maintain a very, very tight color application that the customer demands. So the end customer demands. So this is a very, very doable control methodology to enhance both your color offering and to increase your color uniformity. So it's the ability to really take your color control and color palette that you offer to the next level, and that's kind of what we were hoping to see. I think this is the last slide.
It is, yeah, and we just have our references here.
Okay. And I also wanted to give a little bit of thanks. We inherited this presentation from another person, Chris Ebert from Light Metal Coloring, and he was not able to get it done because he had a whole bunch of other responsibilities. And so he was gracious enough to allow us to fill in and to present this. So thank you to Chris Ebert.